You are listening to The Vocal Technologist. Spoken tech for your ears.
You know, if you look at those old black and white photos of telephone switchboards from like the 1920s, there is a very clear visual of how infrastructure used to work.
Oh yeah, with the huge walls of plugs and the physical cables everywhere.
Right, exactly. You had a human operator physically taking a cable and plugging it into a hole to connect point A to point B. It was entirely manual, completely visible, and, you know, the boundaries of control were absolute. You could literally point to the exact person holding the wire.
And if a line went down, that operator knew exactly which physical connection to trace. I mean, the accountability for the entire system was quite literally held in their hands.
But stare at modern cloud architecture today, and that physical switchboard is just completely gone. We're looking at a landscape that is increasingly abstract.
It's all invisible layers now.
Yeah, and if you're listening to this deep dive, you already know the ground is shifting under your feet. You're the learner. You're the type of person who wants to stay ahead of the curve, understand these tectonic shifts, but you absolutely do not have the time to drown in info overload.
Because there is a lot of noise out there right now.
So much noise. So we are taking a massive stack of sources, specifically a loaded May 1st, 2026 DevOps newsletter, and we're extracting the absolute core of what you need to know.
Our mission today is to map out a boundary that is, frankly, moving as we speak. We're looking for that razor-thin line between what machines can do autonomously and where human intelligence is still absolutely irreplaceable.
And spoiler alert, that line is practically invisible now. We're unpacking a reality today where AI officially has its own credit card, where Kubernetes is getting remarkably self-aware about its own memory limitations, and where a very real 2029 deadline is forcing a complete rewrite of how we secure the internet against quantum computers.
We are officially crossing the threshold from humans using tools to tools operating as independent actors in our infrastructure.
Okay, let's unpack this, starting with the most immediately disruptive news we have in our stack. AI is no longer just a really smart autocomplete that sits in your IDE and, you know, suggests a block of Python.
Far from it.
It is graduated. It is now an autonomous agent that deploys infrastructure and spends real-world money. The first domino to fall here is the expanded partnership between OpenAI and AWS. They are bringing GPT 5.5 and other OpenAI models directly into Amazon Bedrock.
What's fascinating here is the architectural shift this represents. For context, Codex, which is OpenAI's coding tool, already has 4 million weekly users.
Which is a massive number on its own.
Exactly. But bringing it onto Bedrock alongside the new Amazon Bedrock managed agents, it changes the game entirely. Enterprises can now build these multi-step autonomous workflow agents entirely within their existing AWS security perimeter.
So it's not phoning home over the public internet anymore.
Right. The AI isn't an external service they are calling out to over the open web. It's an internal operator acting within their own walls directly on their production environments.
But the source material shows it goes even further than internal AWS environments.
Right.
Cloudflare and Stripe have just launched a co-design protocol that honestly it blew my mind.
Oh, it's wild.
They have created a system that allows AI agents to automatically provision Cloudflare accounts by domain names, set up paid subscriptions, and deploy production applications on behalf of users.
Yeah, they've basically automated the actual commerce layer of DevOps.
Right. But I have to push back here. Handing an AI the ability to buy things feels inherently reckless. It's like setting up a high-speed algorithmic stock trading bot, but instead of trading stocks, it's trading your cloud infrastructure.
It can definitely feel like handing a teenager the car keys and a blank check.
Exactly. You can make thousands of micro-purchases before you even wake up. Isn't abstracting the payment layer away from the user fundamentally dangerous? Like, what if the agent hallucinates and spins up a massive, sprawling global network deployment that costs thousands of dollars?
Well, what's fascinating here is how the architects of this protocol anticipated exactly that hallucination scenario. They didn't just build the engine, they built the brakes.
Okay, so what are the brakes?
The safeguards are the most critical part of this Cloudflare and Stripe integration. First, there is a hard, unchangeable $100 monthly spending limit per provider baked directly into the protocol.
Wait, really? It's hard-coded?
Yes. The agent literally cannot bankrupt you no matter how badly it hallucinates.
Okay, that assumes $100 is the only risk. But what about the identity piece? If an AI gets compromised, can a bad actor trace the AI's actions back to my personal credit card?
That is the second guardrail, and it's brilliant mechanically. They use Stripe as an identity provider to attest to the user's identity, but they use tokenization to keep the actual payment details completely hidden from the AI agent.
Oh, interesting. So the AI never actually sees the card number.
Exactly. The agent receives a cryptographic token that effectively says, I am authorized to spend up to $100. But the AI doesn't know your name, it doesn't know your bank, and it doesn't know the underlying financial instrument.
It knows that it can spend, but the how is completely masked.
Right.
So it's essentially a prepaid digital gift card locked to a specific API.
Exactly. AI is no longer just processing data, it is executing commerce. And to that safely, we need entirely new guardrails like identity masking.
Which leads us into a massive secondary problem. If these AI agents are now out there deploying real infrastructure, setting up accounts, and pushing code to production, well, what happens when things break? Because complex systems always break.
Oh, inevitably, that's the one guarantee in software.
Well, how do we test these wildly complex systems? And more importantly, who is holding the bag when they fail? Our sources point to a piece from incident.io about using AI for postmortems.
Right, the incident response side.
Yeah. Now, they acknowledge that AI is fantastic for the grunt work. It can scrape the Slack logs, automate the incident timelines, draft the initial summary reports, all that stuff. But they warn that the real danger lies in AI generating convincing yet unowned conclusions.
Convincing yet unowned is such a precise way to describe the problem.
It really is. It makes me think of having an automated spell checker write an apology letter to your spouse. Like, sure, it might be structurally perfect. The grammar is flawless. It might even pull specific examples from your text history to sound sincere.
But it's totally hollow.
Exactly. It lacks the actual emotional responsibility required to fix the underlying relationship. If you don't actually understand why you are apologizing, the relationship is just going to break again.
That is a perfect analogy. The spell checker didn't learn the lesson, it just formatted the output. In incident management, the real value of a postmortem isn't the PDF document itself, it's the human synthesis.
The actual learning process.
Right. It's the engineering team sitting down, looking at the failure, and taking personal accountability to engineer a solution so it never happens again. AI-generated summaries create the illusion of resolution without the actual human accountability.
But you can't have that human accountability if you don't even know how your system works under pressure. Which brings us to the philosophy of software testing, specifically some techniques highlighted by Antithesis.
Oh, this part is really cool.
They argue that we have to move way beyond handwritten examples. Standard unit tests, where a human writes a script to check if button A does action B, they just aren't enough when AI agents are operating your infrastructure.
Because a human writing a test is only going to check for the bugs they already know to look for. You are limited by your own imagination.
Right. So Antithesis is pushing for much more aggressive techniques. They mention fuzzing, swarm testing, concurrency testing, and deliberate fault injection. Let's break those down, because this is where the mechanics get wild. Fuzzing, as I understand it, is basically throwing mass amounts of random garbage data at an application to see what makes it crash, right?
Essentially, yes. Imagine a toddler banging on a keyboard, but operating at millions of keystrokes a second, trying every conceivable invalid input to find memory leaks or logic flaws.
Huh. Millions of toddlers on keyboards. And swarm testing takes that a step further.
Swarm testing is about combinations. Instead of just testing the standard user journey, you run tests where arbitrary features are turned on and off in bizarre configurations.
Give me an example of that.
Well, what happens if an AI agent tries to deploy a database while the caching layer is intentionally disabled and a network partition happens simultaneously?
So you're intentionally exercising rare failure paths. You are trying to see how the system recovers from a good crash to surface those hidden bugs much earlier.
Exactly. And we have to link this testing philosophy directly back to the AI postmortem issue. You cannot rely on an AI to magically figure out why a complex multi-agent system failed in a postmortem if you haven't engineered that system to surface bugs cleanly in the first place.
That makes total sense.
Fault injection and swarm testing are how you map the boundaries of your system before the AI agent accidentally finds those boundaries in production.
Which means human critical thinking is required to design the torture tests so humans can own the inevitable failure. That brings us to the actual foundation of all this. If human operators are still ultimately responsible for the stability of the system, we have to look at how the core building blocks are being fortified.
The underlying bedrock.
Right. And in DevOps, that bedrock building block is Kubernetes.
Great orchestrator.
Yeah. And Kubernetes version 1.36 just dropped some massive updates aimed directly at preventing systemic failures. The big one detailed in the newsletter is staleness mitigation.
Which is huge for concurrency.
Definitely. Now, to understand why this matters, we have to explain how a stale cache happens in cloud time. Imagine two controllers, basically automated managers, trying to update the exact same database row based on information they received a millisecond apart.
A race condition, essentially.
Exactly. One acts, and the other acts a microsecond later based on data that is now technically out of date.
And in a highly concurrent system, a cache that is 5 milliseconds old can cause catastrophic deployment decisions.
Right. So the fix in version 1.36 involves adding atomic FIFO processing to client Go. FIFO stands for first in, first out. They're effectively forcing these controllers into a strict queue and implementing aggressive staleness checks in 4 high-contention controllers.
And those are replica set, daemon set, Job, and stateful set.
Yes, the heavy hitters. These are the controllers constantly fighting to manage how many pods are running.
They are forcing the system to verify the cache resource version before it takes action. Measure twice, cut once, but happening millions of times a second.
And they've added a new metric, stale sync skips total, which monitors exactly when a controller skips a sync because it realizes its data is stale. Plus, version 1.36 introduced opt-in memory quality of service, or QoS, with tiered protection.
Which is a fascinating way to triage memory under pressure.
You have guaranteed pods using the memory.min setting, burst stable pods using memory.low, and best effort pods with zero protection. But wait, let me jump in here. So what does this all mean for the average developer?
What do you mean?
Well, if Kubernetes is automatically killing best effort pods because they have zero protection and aggressively throttling burstable pods based on these new memory.low thresholds, aren't we just trading one type of unpredictable crash for another?
I see where you're going with this.
Like, with Kubernetes adding all these automated staleness checks and memory tiers, aren't we just adding more invisible layers of complexity that the developer has to troubleshoot later when the AI postmortem fails to explain why a pod was randomly evicted?
It's a fair question. But if we connect this to the bigger picture, it's actually the exact opposite. Kubernetes checking its own cache and aggressively managing memory tiers doesn't add invisible complexity, it absorbs it.
Absorbs it. How so?
Previously, a stale cache would result in a bizarre, seemingly random deployment failure. Maybe a replica set spawns too many pods and brings down the node, and a human would spend hours trying to debug the ghost in the machine. By forcing the controllers to verify resource versions natively, the system avoids the crash entirely.
So it stops the cascading failure before it even starts.
Precisely. And that new metric you mentioned, the stale sync skips total metric, that is a vital bridge back to our discussion on testing and accountability. This metric finally gives human operators a clear, visible signal when the system is struggling with outdated data.
So instead of a silent, baffling failure, you get an explicit searchable log.
Exactly.
That makes total sense. It's surfacing the problem cleanly. And we're seeing this push for absolute visibility everywhere in the stack right now. The Spacelift guide on Terraform auditing in our sources talks about using tools like Checkoff, Trivy, and OPA.
Open Policy Agent, yeah.
Right, using those for continuous auditing, state protection, and policy enforcement. Even Datadog is pushing for better network testing by using TCP, UDP, and ICMP protocols to exactly match application traffic to pinpoint latency and packet loss.
Because if your foundational infrastructure is murky, any autonomous agent built on top of it will inevitably collapse. I mean, you cannot build automated workflows on a system that lies to you about its own state.
Very true. But even if we perfect Kubernetes, even if our Terraform policies are ironclad and our AI agents are spending safely within their $100 limits, all this infrastructure, literally the entire global internet, relies on fundamental cryptographic trust.
The actual math keeping it safe.
Yes. And here's where it gets really interesting. What happens when quantum computing threatens to break the underlying math that secures that trust?
This is the existential threat to modern cryptography.
And it is no longer a theoretical, maybe in 50 years problem. Cloudflare has just made post-quantum encryption for their IPsec service generally available. They're using the new IETF hybrid MLChem draft standard, specifically FIPS 203.
And they've already tested it with hardware giants like Fortinet and Cisco.
Right. But the real headline that jumped out at me is that Cloudflare has officially moved its full post-quantum security target up to the year 2029. 2029. That is right around the corner.
It's coming fast.
Imagine waking up in 2029 and realizing your entire secure infrastructure, the encrypted tunnels securing your global network, are suddenly transparent to a quantum computer.
It's a terrifying prospect. But to understand why this is happening now, we have to look at why IPsec lagged 4 years behind standard web traffic, like TLS, in getting post-quantum upgrades. For a long time, the security community's focus for securing IPsec against quantum threats was on something called quantum key distribution, or QKD.
Now, I've heard of this. This is the stuff that requires actual lasers and fiber optic cables, right?
Exactly. QKD relies on specialized physical hardware using the laws of quantum mechanics to detect if an encryption key has been intercepted in transit.
Sounds like sci-fi.
It does. The problem is physical hardware doesn't scale to the entire internet. It is wildly expensive and severely limited by physical distance. You can't put proprietary quantum hardware in every single data center and branch office on Earth.
Oh, right. So they hit a physical wall and had to pivot back to software.
They solved the scaling issue by moving away from hardware-reliant QKD and fully embracing the MLChem standard. MLChem, which stands for Module Lattice-Based Key Encapsulation Mechanism, is an algorithmic defense.
Okay, so what does that actually mean in practice?
It uses incredibly complex lattice math equations that classical computers can run just fine, but that quantum computers are fundamentally bad at solving. By shifting the defense to software, Cloudflare can roll out post-quantum protection at a global scale almost instantly.
And we are seeing this desperate push to automate and solidify trust everywhere, not just against quantum threats. Look at the new IBM Vault update we have in the sources. They've just integrated public certificate authorities via ACME.
ACME being the Automated Certificate Management Environment.
Right. What IBM is doing is unifying private and public PKI, public key infrastructure, workflows. For the listener, think of PKI as the digital passport system of the internet.
Good way to frame it.
By using ACME, IBM Vault is automating the renewal and governance of these digital passports across both internal company networks and public-facing websites, all in one platform. It eliminates the manual processes where a human glazes over, forgets to renew a certificate, and brings an entire site down.
If we connect this to the bigger picture of our entire discussion, what is actually happening here? From AI agents using Stripe tokens to mask their identity, to OPA policies in Terraform, down to automating public and private PKI via IBM Vault, every single layer of the stack is desperately trying to automate trust.
Yeah.
We are trying to mathematically secure these environments, delegating the intense cryptographic burden entirely to machines before the systems become too complex for humans to secure manually.
Which fundamentally changes what a human developer actually does all day.
Yeah.
If the AI is writing the syntax, if Kubernetes is managing its own memory, and the system is handling the complex lattice math for quantum security automatically, the developer isn't really writing code anymore. They're just dictating what they want to happen.
That shift from writing syntax to purely orchestrating intent is the entire premise of vibe coding.
Ah, which perfectly explains why industry leaders are completely rethinking developer productivity. Gene Kim, the author of the DevOps Handbook, is hosting a DevX Summit with Google Cloud and Okta, and vibe coding is a central topic. When the machine handles the how, the human is only responsible for the why. The developer's only job left is to define the outcome and hold the system accountable. Wow. All right, let's bring this all together for a rapid-fire summary. We've covered a massive amount of ground today. We saw how GPT 5.5 and Codex arriving on Amazon Bedrock, along with that wild Cloudflare and Stripe protocol, are turning AI from a passive coding assistant into an active financial and infrastructure participant, complete with tokenized identity masking.
And we looked at the fight back against systemic complexity. Kubernetes version 1.36 is aggressively mitigating stale caches with atomic FIFO processing and adding strict memory QoS tiers.
While testing frameworks like Antithesis are pushing us to fuzz and swarm our software, intentionally injecting faults so we don't have to rely on hallucinated, unowned AI postmortems when things break. We need to surface bugs cleanly so humans can take real accountability.
And finally, the ticking clock. The 2029 post-quantum deadline is forcing a massive upgrade in how we orchestrate cryptographic trust.
Shifting away from unscalable hardware solutions like QKD to scalable mathematical software standards like MLChem, while platforms like IBM Vault bring public and private certificates under one automated roof.
Exactly.
Which leaves us with a final, rather difficult question to mull over. We spent a good portion of this deep dive discussing how humans must retain ownership in incident response, how an AI postmortem is just a convincing yet unknown conclusion. But we also just established that the underlying cryptography and infrastructure are becoming so mathematically complex they require automated MLChem systems and strict Kubernetes controllers just to function. As our security, our infrastructure, and our payment layers become strictly mathematical and algorithmic, At what point does human accountability become an illusion? Simply because the systems are too vast for the human mind to actually comprehend the postmortem.
It's the ultimate paradox. Are we truly holding the system accountable, or have the systems simply become too fast, operating at a scale too massive for us to even know what we're looking at?
A chilling thought to leave on. Are we still the operator at the switchboard, or were we just watching the lights blink, assuming we know what they mean? Thank you for joining us on this deep dive. Stay curious, keep questioning the systems you build, and we'll catch you next time.
Spoken Tech for your ears.